Welcome back to the Structural Engineering Podcast. This week, we talked with Jeff Thomas with BHB Structural, located in Salt Lake City. We dive into the world of facade engineering and one of the most important concepts behind successful building performance, movement. While facades often appear rigid and permanent, they're constantly responding to wind, temperature changes, gravity, construction tolerances, and even seismic events. Accommodating that movement is critical. And when it isn't considered properly, the results can be cracked finishes, damaged components, water intrusion, and costly repairs.
In this conversation, we explore how facade engineers think about movement, the role of slip joints, and the coordination required between everyone on the project to make a building look and act correctly. We have a great conversation packed with real-world lessons and details that can help you get through the facade. Let's get started.
The Structural Engineering Podcast.
How did you get into this world of facade engineering? Like, what does that look like? You said you've been at BHB for about 10 years.
Yeah.
You kind of fell into it. Did you get hired to just do that?
Yeah, well, so I should give that preface. As I mentioned, I do a lot of different types of projects. And on some of those, when it's a type of building that has the metal stud skin with some type of facade on it, I'll get to do that facade design. I know enough to be able to speak to architects about it well. And when I'm talking with other structural engineers, that's where I'm going to get a bit more tested on that knowledge. But we have a couple people at our firm that are very, very deep into it.
Calcbook version 2 is here. This is a major step forward for the platform. Not just a new look, but a rework of how calculations come together.
Calcs can now link to each other through LoadPath. Projects are easier to structure and navigate with a new Project Explorer, and their upgraded Beam Analyzer brings advanced FEA directly into your workflow. Any load, any support, anywhere on the member.
Promo code SEPOD for 50% off 3 months at calcbook.com. Calcbook version 2, out now.
I would say the person who's the most knowledgeable that I know, Chris Hoffines, he does a lot of work for the Church of Jesus Christ of Latter-day Saints with their temples. And those projects have the next level facade design on them. And so that's where I think in part the genesis started, is these more institutional clients like universities, state of Utah. When you work with a developer who might just be trying to turn around the project and sell it off, I shouldn't use the word like that. When you work with a developer who is trying to do that, because there are developers who do want to have that longer term holding, they may be less concerned about how the skin interacts. And so if you come to it with a mindset of like, oh, I just did this temple and now I'm going to do this spec office building, and you're like talking about all these movement joints, they may be like, wait, what? What are you talking about? And there is a certain increasing of the standard over the years. Hearing Chris tell this story from when BHB first started designing the metal stud skin along with the rest of the building, because that's, I think, ultimately the point we were trying to make to these architects in this seminar, is that we believe that you're going to save the owner money by not doing a delegated design on the building skin, and by having the engineer of record who understands how the building moves, how everything deflects, take that on, include that in their scope, you'll end up with a better product. So to kind of wrap that around, doing even the spec office building where the developer may not want to pay for some additional level of service, there's just a certain standard that we've been doing for a long time, and we start to see that creep in to the rest of the market, where you drive around, you see buildings that are framed with this type of skin, and okay, like this is catching on, because it really, to do these detailed movement joints, it doesn't have to add a lot of cost, is like the fundamental thesis.
From a construction standpoint or a design standpoint?
I would say both. If I back up for a second, just introduced the idea of the metal stud skin and the type of movement joints that we'll account for. So you have your 5-story office building, and they want to have bands of windows at each level, and they want to have some type of metal panel or brick veneer that contrasts those windows at each story. Because each level will drift a different amount than the level below, a really important component of seismic design or even wind design is to allow for some amount of slip between those levels. And that's usually accomplished by a combination deflection slip track that's at the head of those windows. At the head of the window, because the joint is less noticeable, there's already the window there, so it cuts across. And then it would continue through any like vertical segment of skin of veneer that's present. So if there's brick veneer, continue that joint all the way across. And so this will allow each level to slip independently of the other, as well as the deflection of each floor, like the perimeter beam conditions can deflect down in that same track. So you accomplish a couple things with this type of design. There are quite a few firms who will say, okay, I did my building design, and now I'm going to pass off this skin design to a third party, a delegated design, and I'll note down how much wind force, how much seismic force I have on this skin, and I'll note down how much movement they need to plan for. And so what at BHB we're advocating is that structural engineer of the building takes on that whole thing and does this skin design as well. And so if we're comparing this to, say, a wood frame building where we don't have movement joints, we're just accounting for your shear walls to move and provide enough stiffness that your veneer doesn't end up being a major contributor to force that's taken that you don't intend it to take. When we're working with these steel buildings, which is most often that have this type of skin, it's a more flexible system. Moment frames, BRBs, there's going to be more movement present. And so we can't just frame between each level like you would with a wood structure. Or well, you could do that, but now you're having to design your metal stud skin or the weak axis bending that would take place if that stud spans between the two levels. And it's called a weak axis for a reason.
Right.
We want to be able to use those studs in their strong axis as much as possible, resist the out of plane wind and seismic loads, then make that joint to allow the movement. Now, I have seen certain contractors that maybe have more of a background in wood framing build the metal stud like it's wood, despite our details.
Yeah.
And that's definitely it's more common in 2-story and below structures. There's less movement to deal with. So you can
probably different contractors that would comfortably do that size of building.
And yeah, and maybe they're more used to that. And then when they get to a 3-story plus, now they say, oh, well, we did it like this on this other building. So, we don't need to look at the details. We'll just do it this way. That's when extra cost comes in. But realistically, when we do this type of like spandrel detail, when the metal stud cantilevers below and above the edge of deck, you don't have to have header framing or jam framing. You just design each metal stud along the edge of the slab or that cantilever, and then you have your track where your window or whatever is attaching to. But we don't need some beefy box header because each stud takes that load. So that's kind of a roundabout way of answering your question about cost. It ends up being pretty, for a bigger building, I would say even more economical.
I had interesting, in my career progression, I don't know if other people assume this, but what was in my head is once I'm getting to these larger buildings, the main structural engineer doesn't do the skin design, and like somehow I felt cool about that I've
Oh,
I don't know,
sure.
Yeah.
why,
Sure.
but as when
No.
you're whatever 25, it's
Or
like,
the
oh,
connection,
yeah,
Well,
design or the stair design, right? Everything's just delegated.
that's the part that I thought of when you're mentioning this is I know on like the east side of the country that connection design
yeah,
is
super.
frequently delegated. And I do think that there is some wisdom there. It's like I don't know, I think it's Plato that gives that example of you have a town where if there's only a couple people, then each person has to do like some of everything. But the more
Mhm.
people that come into this town, like, well, now we have a guy that just makes shoes and he can trade the shoes for food. And
Yeah.
like over as a society grows larger, we're going to have more specialization.
Oh, yeah. This is a section called City of Necessity in Plato's massive statement, The Republic. I feel like a discussion recently, we talked about the allegory of the cave. It's sort of perception and how we make truths with the facts that we are sure of. There were some air quotes around that. Anyway, I'm cutting myself off. Cool idea. That's where it is. Back to it.
And I think the main thing that I would argue here is that we want to be very aware and intentional about how we choose what to specialize in and what we give away. If there's certainly times where an owner really doesn't want to pay that upfront cost. They see a fee and they say, oh, hey, like this fee is too high. And in that case, maybe there are some components that I could say, okay, we can delegate these. It may not cost you less in the long run, but you may be able to feel better about the fee at the start.
Yeah. When
So
you do the veneer design in-house, is it competitive and like just nearly the same, or can it be a little bit less than subbing that out? Because, just like as information has to move on, you still have to put the info together and then send it out and then review the drawings. So there's a lot of steps in there.
right. I firmly believe that at the end of the day, from our budget and time perspective, that we're able to have a net benefit by keeping the skin design in house.
Yeah.
From the standpoint of what you're saying, packaging up that information, but also when it comes to going out on site, I'm already there to check out other parts of the building. And if I can also take a look at what they're doing on the skin, if I don't have to try and figure out what a submittal is doing that's different than what I thought they would, all of that is time savings.
Yeah.
Yeah. Starting at the beginning here, for people listening that have no clue what a facade is.
Yeah.
Yes. We'll set some groundwork.
Or
I guess even further back than I would. Yeah.
yeah. So or people that maybe they are that engineer of record that delegates everything. What would you say makes up the facade, or like what's the parts and pieces that we can like make that mental picture, take that
Sure. Yeah. So the term facade, I think, can sometimes mean like fake, but how it's often used from a structural or building standpoint is it's what you see from the outside of the building. So whether this is brick veneer, some type of stone cladding, metal panel, could be a rain screen system. I mean, even something like ephes or stucco, like those are all types of facade or finish systems. The ones when I'm talking about facade, it's more of those either heavier or more specialized types of material. So if it's brick veneer, stone, metal panel, rain screen, because it's more of a product, there's more that needs to be done to accommodate it at the point it attaches to the structure.
Do you have more architectural coordination, do you think, on the veneer side? I was just, when you present a building, the thing you see is the veneer.
Right.
And so I would wonder if there's a little more intense, like they want to make sure that you are producing exactly what the architect has in mind, compared
Yeah.
to the bones of the building, like if it stands.
Well, and it really depends on the size of building and the performance out of it that the owner is looking for. There's projects where we'll do our our standard of let's make brick tracks and these slip conditions, deflection, and there's not a lot of coordination that takes place. Either that's because we're working with an architect that knows well our details and knows how to account for that, or it's just not something that's as high of a priority, which is not ideal, but it sometimes happens. And then there can be these very complicated structures where, especially if the owner is aware of seismic activity and they know that we want our building to be either like immediately occupiable or have very little repair necessary after a major earthquake so that they can get back up and running. In those cases, there's like very intense coordination. This can be, noting, okay, we're going to have like what we'll often do on our plans when we've done this skin design for facade is we'll provide an elevation view that shows where slip joints are going to be. And that can include if, say, that you have windows of two different heights, and we would have a slip joint at one lower elevation, and then we need a slip joint at a higher elevation. Well, now you're going to need a vertical movement joint between those. So that now it's kind of like if a building's moving, it'd be like a jigsaw puzzle trying to
Right.
fit together. So we provide that vertical joint. And those are often a little more of the concern from an architectural side because they have to have something like if we look at brick veneer, for instance, there's a 3/8 inch line every 4 inches. So it's pretty easy to just like instead of using mortar, put some
Just
type
kinda
of
hide it.
joint in there, and now you have a horizontal joint. But if you need something vertical, that doesn't always fit in as well with an architectural facade. And so
Right.
that's what would need to be coordinated.
Yeah. So when we're thinking facade design, it's not, my mind originally goes to the backing of it. That's metal stud or wood stud or, that system, girts or something. But you're talking about the actual design of the panel, the brick, checking the stresses and bending action, and then putting joints in the actual material itself, not joints in the structure, the metal stud and the behind it necessarily, or both.
It'd be both in that we want it to all work together.
Okay.
And so you asked what is facade, and I've been using this term skin. So it's like we have facade on the very outside, and then we come in and we have some type of skin system, and that's what will support that facade, specifically between the stories of the building. If we're talking about a steel structure, there's not actually structural walls. There's moment springs, there's brace springs. You don't have something to attach your facade to. So we have to build I don't like to say non-structural wall because it's still
It makes it sound less.
in seismic load, but it is a non-bearing exterior wall that will help carry that load and transfer it to the building structure.
Can I ask, since you had just said transfer some load here, when you're designing facade, what are the loads that we are focusing on? Like, I know, wind, some out of plane movement of this. And then is most everything else just forced deflection from the building moving?
So yeah, it's a good question because ideally with proper jointing, we're massively limiting any type of force from deflection of
Yeah.
building movement. So then it is just the out of plane load that would be on it. So the wind or seismic load is what we would design the skin system for. And that's even to say it often excludes gravity load when we're dealing with heavier facade systems. So often when we do a brick veneer system or like a stone cladding, then there's a heavy steel like angles or channels system that attaches back to the building deck that will actually support that brick veneer. with a ledger angle that runs along. And so then the skin, which I may have said this, but often is done out of metal stud as a non-combustible material. Given when we're talking 5 stories, then you're going to need to be some type of non-combustible material. That skin would just have the veneer anchorage back to it to take like any type of wind suction or seismic force.
Is there a big part of facade design in the beginning, like the geometry of how all this can work together? Feels very engineering, but it's not the geometry that we're used to for a building. It's like, where do the joints align and how far can we go, and trying to overlay this on the building geometry.
Sure. I think it depends on the sophistication of your architect.
Yeah.
If this is something that they've done a lot of work with, then they may just, it's like with a column layout. If you have an architect that has worked with structural engineers for some amount of time, they know they're not going to put like 50 feet between columns in an office building. And so same thing with the facade, that they're going to have some amount of pre-considered notion of where joints might be, where we'll want to put slip planes. And then it would be especially, well, I think even if you're going to delegate the design of the skin, then it would be very, I would say, dictated by code that the engineer of record needs to account for how the building will move and how that will translate to the building skin. And that's, I think, where the elevation view is a good layout, so that you can map these slip planes, you can see if there's a conflict, you can imagine the building moving, and then account for that.
So what is it? I'm like thinking in my head, projects I've been part of that seem to very blatantly or obviously have someone that's designing the skin, that's part of the team, or it often maybe happens without us fully as engineer of record knowing that what they're doing. Right, we don't always maybe review the joints they're putting in there or things like that. But what does it look like when that doesn't occur? I mean, what in the code drives the contractor to hire someone to design the facade per se, or what could it look like if they don't design it?
Sure. And I'll try and find the reference from my presentation. There's some sections in ASCE 7 and the IBC that specifically say that the building needs to be designed to account for movement. I think, let's see, ASCE 716 15.5.3.8, connections and panel joints shall allow for story drift caused by relative seismic displacement. Like, this is the code that we all use as part of our building design, has these sections that just haven't always been super closely enforced. I think that's anybody listening to this that says, holy crap, like I didn't do this on the last building, like what's happening? Like it's not something that's always checked from a plan review side. And even though that's not like the be all end all, if a firm has never had that comment come up and never heard this talked about, then you might not be designing for these specifically. But your question was about what might cause a contractor to engage someone for skin design.
Yeah.
I think, it'll come down to how are you going to support the facade at the end of the day? Like that, someone will need something to do that. And when you get tall enough, like if it's just brick veneer and you're, say, 2 stories, you can just bear that down on the foundation wall. But once you get above 30 feet, now that brick veneer needs to be supported, not just from a gravity perspective. So that kind of kicks this into this other level. I think.
Do you think the 30-foot?
What's that?
The 30-foot support that the TMS states, do you think that is on the EOR to provide that re-support? I'm just curious in this world of, again, dividing out responsibilities.
Where does it fall exactly?
Yeah. I know from our firm's perspective, that's what we consider it as. Like, that's our responsibility to coordinate with the architect. And maybe that if that's not common industry practice, then that may just be like us providing an additional service. You might, yeah, given that it's in the TMS, it's hard to argue that it's the architect that would do it. So,
Yeah.
but I have had architects like know about that and bring it up.
Structural calcs don't stand alone. The beam feeds the column feeds the connection. Calcbook version 2 is built around that reality.
LoadPath links your calculations across Calcbook. The new Project Explorer makes navigation effortless. Calcs are searchable with a full table of contents, and the upgraded beam analyzer handles any load case you can bring to it.
Calcbook. Calculations without the black box. Code SEPOD at calcbook.com. 50% off 3 months. Calcbook version 2. It's out now.
There was actually this kind of cool detail where they wanted taller brick, but it was a wood building. So they went up to 30 feet and then they went to thin brick, and then they had like furred out stud to make up the difference in thickness. And it was a cool detail and
Clever way to make it look right. And
it's 30 feet in the air. No one's gonna like look and see, oh, that's thin brick. Like, so
that's genius. Yeah, I was
Yeah.
thinking too, if the architect said, hey, make sure you support this at 30 feet, and the engineer of record didn't consider that, that perimeter support beam is likely very undersized from a deflection and definitely a strength standpoint if they're not anticipating vertically supporting brick above. So
totally.
I would imagine that's on the engineer of record.
That's the thing. It's a heavy load. And I guess this may go a bit beyond your question, but if we're saying like, why is this important? From a life safety perspective, likely there's going to be some kind of veneer over your entrances and exits. And if we don't account for it, then that could break off, either fall on someone who's trying to exit the building or block the exit. And now, even if the rest of the building, like structurally, is standing and you're like, hey, this building did great, but now nobody could get out, then that's a problem.
Yeah, that's actually what I heard. The last big earthquake in Alaska, that they had a few schools, I believe. Don't quote me on that, but a few schools that everything was pretty good shape except the veneer over the exit doors fell off and blocked the exit doors. And I heard that's what's been,
like, make sure that stays up.
Yeah, right. And I've heard that's maybe the bigger reason, especially on the West Coast, they're pushing, making sure the design is fully vetted and someone has checked that the brick ties actually work at the right spacing is from that. There may be more, situations, but from that earthquake.
Well, and the difficulty with this whole topic is that, one, it's not taught in school, so you're going to need to learn on the job. And I was doing a bit of research before this to see like what resources are there out there. It's not that many. I found a Structural Magazine article from 2017, Challenges in Cladding Design. I found like a one-page brief article by Chris Hoffines from my firm that's talking about skin design. And then there's this article with Interstate Brick that KPFF put together that's more about like anchored brick veneer and various ways. And that one's like very detailed and very in-depth. So definitely, even if there's not a lot of resources, there are some that we as engineers can look into to help be more knowledgeable about the topic and better serve our clients and their clients.
The ones I could find are in the show notes. Check them out.
I had a question pop in my head. This is going back a ways in the discussion, but I'm curious. If you're the code reference for you must design the skin for building movement, if you're designing the skin for someone else's building, how often are we just looking at like the code maximum movement and making sure we're good there? Or is this so for BHB, if you're doing one of their buildings, you know exactly what the movement expected is. And so you can design to that number versus just the most it can move. Like,
right. I mean, if you don't have the information about movement and the engineer of record is unresponsive in that regard, then that is what you could use.
You have to do. Yeah.
The problem depends on, well, Yeah, in part, a problem comes from the system that is being used. Like if you have a masonry shear wall structure or concrete shear wall structure, then your movement is going to be much lower than that maximum. And so now you have this big discrepancy between actual movement and what the code maximum is. And you'd end up with these like very oversized conditions. Versus if it's a moment frame, then you're often designing to that brick limit. And so then that may be a little more appropriate.
From a facade standpoint, what deflection limits are you designing for? Often maybe brick is that L over 600, but with wind, not necessarily having a codified serviceability limit, seems like it's really up in the air. That 10-year MRI guidance versus 700-year, in the appendix that is talked about in ASC 716. What approach is there for wind?
So I'm trying to think of a specific guideline to give on the wind side. When you asked that, I thought of a recent Structure magazine article. It's updated design recommendations for brick veneer on cold formed. And essentially the TLDR is that L over 600 is probably more appropriate as a range between L over 360 and L over 600, depending on that required performance. If we're talking about skin deflecting out of plane, because that's a slightly different behavior than saying we have a lintel that is either above or below that brick and needs to deflect down. Usually we're often using the IBC deflection limits just given in, forget chapter 16, but somewhere.
Yeah.
And that from an out of plane perspective, unless you have a very specific product that you're trying to support, like we'll do some more specialized rain screen. And at that point, you're trying to get a basis of design. Even if you don't know exactly who the manufacturer is, you'll look at that and see, here's what deflection we need to account for with this system. Because that's the ultimately, like, other than brick, which is very much a commodity in a sense, a lot of these other things you're doing skin for are more of a product, and that has some associated information with it.
Yeah. So yeah, I get that's the, I guess, capacity side of the movement, but from a demand standpoint, is there best practices from a reducing your load like we can often with IBC for CNC loading? I mean, I guess kind of just the same thing from a mean recurrence standpoint, is just utilizing maybe that lower load from a deflection standpoint.
Oh, I see what you're saying. That because this isn't
a main wind force.
Yeah, we're not trying to make sure the building stands up. I think there's an argument there. For me personally, I would go back to that side of this is a life safety concern in a lot of cases. I think so I would say the standard that I'd operate on is to just not have the reduced load and use a basic components and cladding assessment. And then if there was maybe a value engineering exercise that's going on, then perhaps you could look at considering a different recurrence interval.
Okay. Gotcha. Yep.
Yeah.
That makes sense. So what kind of drifts could be many, many, many inches? Like you said, moment frame system. What size of joints could we be talking about, let's say, with a few of these different systems, both from a vertical joint standpoint and a horizontal?
Sure. I would say like vertical joint from deflection, trying to stay around that 3/8 line when we're talking about, like, that works really well with a brick veneer to have the same kind of joint as you're going to have in the rest of the brick. If you have like more of a metal panel system, that maybe it can be designed to have some type of split between the two panels, like vertically. Now you could allow for something a bit more, where maybe that's a 1/2 inch, or, I mean, it'd be hard to go bigger unless you have a specific system that, can accommodate that. Because I've heard even I think it was a moment frame building where they did initial, no, I think it was a brace frame building, and they did their initial computations, came up with something like a 2-inch joint that was going to be necessary, and they had this like fancy Italian marble facade.
I bet it didn't
And
like that.
yeah, they're like, wait, a 2-inch joint in our fancy facade. And so then they ended up going to a base isolated system to reduce
Wow.
the drifts so that they could. Now, it's not a project with my firm, but it's up at the Utah State Capitol. Like
Oh,
they're not gonna get rid of the fancy Italian marble. So, they're gonna find a way to reduce their drifts.
yeah, I knew they had fancy marble and I knew that they were base isolated, but I didn't know there was any connection there. I was like, this is what Capital looks like, and it's base isolated just in case.
Yeah. No, and it's the North Museum building that they've just put in. So it's like the newest building on that campus,
Yeah.
uh, and ends up matching the base isolated system that's under the main Capitol building, just based on trying to make things work with their facade.
Could we, I'm curious on the joints, like, can you describe what they look like mechanically? How does the joint work? Like, is it a channel interlocking
Oh,
so that
yeah.
water
Yeah.
can't? Yeah.
So our a vertical deflection track, maybe most people are familiar, or some people are familiar with, say the top of a non-bearing wall. You have your metal stud going up, and then you have a track sitting over the top of it with a gap between the top of the stud and the bottom of or the underside of this track, and so then that can deflect down and allow for movement to happen. And you can either, if it's a slotted track, you might have screws in the side that are in slots so it can deflect vertically. If you're going to a flip track that also takes into account deflection, now you don't have any fasteners between the track above and the track below. So you either have a doubled up track so one's a deep leg track over the top of the studs that is screwed to the studs. And then a shallower track nests with the deep leg track so that then that can move down without the attachment, but the studs are still all fastened together.
Mm.
A simpler detail, you can put blocking between those studs and eliminate the deep leg track so that now you don't have this like extra little bump that can kind of mess with drywall. So those are like the horizontal joints, even though it moves horizontally and vertically. When you get to where you need a true vertical joint, where you have a difference in window heights, or if you have the slip track abutting something that doesn't have joints in it, like a multi-story curtain wall. Now you make almost, sometimes we'll call it a crush zone. So it's an area of metal panel that would be adjacent to that curtain wall, so that now, say it's brick veneer for most of your line, and then it comes up against this curtain wall. Well, you want to be able to allow for that horizontal movement difference between the sliding or the brick veneer that is sliding with that story and the curtain wall that is going to be designed as its own system. So having some kind of similar system where you have nested track can provide structure, but then on the outside, the architect may account for like metal panel or something that is like more sacrificial. Or maybe they can make a joint. There are some products where it's kind of like an expansion joint you would see at a stadium or airport that can allow for overlapping movement at those spots without some type of crushing.
Probably a good time to say that we have links and graphics that Jeff sent over that might clarify this. I certainly like to think in images, so it definitely helps me. Check out the show notes.
What and where are we attaching back to in the building? Like, is it very common to be just at the floor level where we have a perimeter beam and that can take a lot of force?
Yeah, usually there's an attachment at the edge of deck. So you have your deck edge angle, or if it's PT, then just at the edge of that PT slab, in the case of metal deck, you'd have a deck edge angle that you can weld clip to. If we're talking about this multi-story skin system, then you'd have a stiff clip attaching to the stud to each of these metal studs at that deck edge. And then because this is a cantilevered system, so you're cantilevering from that edge of deck up to the underside of the window. And then below that edge of deck, you'll have a horizontal stud that goes from the bottom of the adjacent beam out to your metal stud skin. And so now you have two supports. And so you can cantilever from edge of deck up to underside of window, and then down from the underside of the beam to the top of window. That does mean that you typically want to have deeper perimeter beams so that you have a more spread out force couple for this attachment, and usually like some type of kicker that goes back from that beam to your floor deck, so you're not putting your wide flange and torsion
Twist. Yeah.
But that's a typical attachment system if we're talking about this, like where metal stud skin is tied to each floor and isolated from the adjacent floors.
Is that on either standpoint of the stud walls flying by versus inline framed?
So if it's inline framed, then you have a little bit trickier detailing to get the top cantilever to the window above that slab, because now you need a stiff clip to resist like a rotation.
Yeah.
As opposed to a stiff clip that's just taking an axial load in a flyby condition. But that it is a good question to ask, because depending on your fire rating, if like say your first level has a different fire, it has a 3-hour fire rating requirement versus an hour at your upper levels, then yeah, you're not going to be able to fly by, and you'll need something to interrupt those two.
I got a question on a graphic that I had seen in the presentation actually that you did. So horizontal joints can be discontinuous, I believe. How does that work? I'm picturing, this whole building just sliding in a way that it's not going to. But I'm just like, a joint in my head must be continuous. Is that not exactly how I should be thinking about this?
Well, and that's probably the biggest challenge with this type of skin design is these areas of discontinuity.
Yeah.
Whether I'd say the common scenarios are you have along a given floor line, you have windows of two different elevations, because if we have our split plane at the head of the windows, now that makes a discontinuity. Where you have multi-story curtain wall that would interrupt a band of veneer, because the curtain wall, they designed that within its own frame, since that is like very much a product, they'll account for deflection in the frame of that window. Since the glass isn't going to move, you need to design the frame around it, the mullion, to rack and have enough gap. So that would discontinue this horizontal joint. Or if you have a different type of veneer system that maybe can't have joints at the same space, it could be some type of panelized metal system or a stone. And so at those points, that's where at the interruption of the horizontal joint, you provide a vertical joint with one of those crushed stones so that you can move against this area that isn't moving the same as each level. Does that make sense?
Yes, I think.
Yeah.
I'm going to say yes, and then I'm going to think about it more.
I think it makes sense. I'm thinking through especially the crunch zones. I've never heard it phrased that way, but thinking through like the high seismic detailing and sitting in, and one of the webinars or presentations from Simpson per se, and they talk about their seismic drift clip. And you're like, okay, so this wall moves independently in its plane with the building. It's allowed to slide in that direction. This clip maybe has vertical slots as well. Okay, so I get some movement there. And I've always thought as that building's opposing, or the walls opposing the movement of the building, they're sliding against each other, what is happening at the corners where walls are intersecting? And now my mind, and this is where my mind's been just sitting here thinking through this, is like, I guess those corners are crumpling, allowing that movement to occur, I guess, or just mega joints are being added. I don't know.
I say too, like that term makes me think about it like a reduced beam section moment frame. Like it is going to fail, but it is not going to fall down. It is going to yield is the correct word, not fail. And I haven't thought about this logic in a veneer style system that like it just needs to not be harm to people walking down the street, but
it can be replaced.
Yeah.
Totally. It's definitely a very complex topic, especially at the corners. You could have a whole discussion just about how to do those corner details. And I think, and this more broadly in the industry right now, the term performance-based design is being more and more used. I don't think it necessarily needs to go to the level of like, hey, let's use ASC 41 and do this whole a whole design. But if you're asking yourself, if you're asking the owner, the architect, like, what do you want out of this building? Then that can allow some of these gray areas in the code a little more clarity. Like if they don't want to see any damage at the corners during an earthquake, then we need to make some special joints. Maybe you offset a vertical joint back from each, like several feet back from the edges of the corner. If that's more visually appealing than having like a big old joint at the corner. And then that allows for some of that crushing and differential movement. But all of this, a big piece comes down to what do they want out of their building? What level of detail in your drawings are you providing in your scope? Because that's like, I do think that including this design in your scope will be more efficient in terms of reducing construction headaches. That is in the average case. I would say if you're providing a very high level of detail when it comes to the skin design, you should be accounting for that in your scope anyway, whether or not it's delegated. It's going to be more complicated if they have higher requirements.
Yeah. Do you have a common detail that you see not done correctly in the construction side?
I would say the wood framer that decides he's going to bid on the metal stud skin project and try and build it like a metal or a wood header in between, have no slip joint. That's and it's a rough one because I don't know if you've reviewed metal stud submittals. Often it's just like a list of sizes. It's not like, okay, here's how we're going to lay it out all through the building. And so then you go out on your site visit and, hopefully you get there on the first floor. I don't know about you, but contractors don't always tell me when they get to the spots that I ask them to. And that's a rough detail. I would say the other one is when you have a slip joint. A lot of contractors, I appreciate the ones that want to fasten things together well. It's much better than folks that don't have enough fasteners. But when it comes to a slip joint, this is an area that we don't want them to fasten together. And so that's a great point to have a pre-construction conversation and point out these details and say, hey, if you've worked with the contractor, great, maybe they'll do it well. But if you haven't, then have this quick conversation, point out those details and just see if they have any questions, and you'll save yourself a lot of headache.
Yeah. So on the same side, almost for the designers that are getting into this, what is the common design error that you're seeing? For new engineer or someone that's just getting started.
Yeah, I think that the level of detail that you want to look at designing these multi-story cantilevered skin systems, there's a module in Simpson CFS, Simpson's cold form steel tool, that allows you to do this type of spandrel double cantilevered condition, and just making sure that that's that has the appropriate force on it, that the connections are designed appropriately, because like one thing that I learned recently is that you're not supposed to use power actuated fasteners in concrete or masonry in seismic zones.
Ooh,
And
also learned that just now.
so that's one that, well, I should say like above seismic category B. There's some uses in B, but anyway. So like that's one that often in the Simpson catalog it says, oh, just like fasten this with your PAFs and you're good. But if you have a PT deck, then you're going to need a different type of fastener. I have seen some folks do like a RAM Elements model for this multi-story skin condition, because really it's kind of like a spring where these two interact. And I won't try and explain this in audio format, but you can definitely go into a lot of depth depending, again, on what type of performance you're looking to get out of the structure.
So, Jeff, what question have we not asked yet that you think would be good for the listeners?
Yeah, that's a great one. I think
We end on the hardest one.
yeah, for real. I'll say just quickly that, I'm advocating for the engineer of record to also do the skin design. But if you don't, then what does your conversation with that skin designer look like? Is there one? Because I think what we're talking about here is ultimately building performance, trying to reduce headaches. And if you're able to talk with that delegated designer, just like if I do a side plate system that's a delegated design, I'm going to talk with my side plate people. So that's, I think, like another great takeaway. If your firm doesn't want to get involved in skin design, at least see if you can talk with that skin designer.
We had one little question from a discussion we had before, and I think it really fits well in the episode. So, Zach, take it from here.
What does it look like to come in after a building's been built and you're reskinning the building? What is that? What other considerations are there? Give us the high level.
Like if they mess something up, or if you're trying to like
it's an existing building. They're going to
6 years old,
re-facade.
it needs new. Yeah.
Oh, sure.
You really have no designer to talk to.
Yeah. I mean, that, again, depending on the performance that's requested, like if this is supposed to be a high performance building, you may have to go back and do some lateral calcs to know how much is this building going to move, how much are beams going to deflect, because that, especially if it's older, may be a big part of the challenge. So that's a tricky one. I guess you could, if you have the leeway, you can just make the joints bigger, but
Yeah. A little more
Right.
cushion just in case, because you have to guess some things here.
totally.
Yeah.
Well, Jeff, it was good getting to know you here and also talk about facades and skins. And I think Max and I both learned a lot. So thank you so much for taking time to be on the podcast with us this week.
Yeah, thanks, guys. This was great. Loved your podcast.
I've got one other great resource to slip in here on slip joints, or anything from this episode that you want to learn more about. Jeff was at the Coldform Steel Expo right after we recorded. He talked with Kristen Zadel of Neville Wall Group. They focus on wall systems, and she volunteered to answer any question a listener has. So her email is in the show notes. If you want anything clarified, she is a great resource.